Section 5.6 talks about work and fluid pressure. We're going to focus on just work, and specifically if you have a spring mass system. So if you let the mass sit at rest, this is the natural length of the spring. If you stretch this, or compress this, it works the same way really. If you stretch or compress the spring, then Hooke's law says F equal kx, where F is the force that you apply. It could be weight, it could be you're pushing it. K is spring constant. This is like how stiff the spring is. Of course, different springs have different resistance. And X is the stretch or compression beyond its natural length. Now, some of the units that the books use, those are given in the problem. And work equals force. Force is right there. Force times distance. Well, if the force is constant, then you just multiply the two. But if the force is not uniform, if it varies, then the work would be the integral. This would be the equivalent of distance, and this would be the force. So since it's varying, the integral will figure out at every fraction of a foot or an inch or a centimeter or a meter, whatever you're given, how much work is being done, and it sums them up. So the different forces, different variation of the forces are added up. An example of that, a spring has a natural length of 8. So this spring, if you are to let it sit still, that's 8 feet. That's its natural length. And a force of 5 pounds stretch it at 2 feet. So if you attach to it a force of 5 pounds, it's going to stretch at 2 feet. So basically, you start with F equal kx. You always want to figure out how stiff or resistant is this spring. Well, 5 pounds stretched at 2 feet. So the force, the spring constant is 5/2. And now we know that the force for this spring is 2.5 times x. Find the work done in stretching the spring A. From 8 to 10 feet, work would be the integral. Well, since it is natural length is 8, so when you say from 8, that's 0 to 10 feet, that's only 2 feet worth of distance. And f of x is 5/2 x dx. And if you work this out, that would be 5/2 is a constant, x squared over 2 evaluated from 0 to 2, and that would be 5/4 times 4 minus 0, and that would be 5 feet pounds. B, how about if I wanted to move it from 7? Well, since it's already 9, 7 is really 1 inch inwards to 9. So I've got from 7 to 9, that's 1 to 2. Again, whether you compress it or stretch it, it's the same deal. And we already know the stiffness of this system, and that's basically it. So work would be 5/2 x squared over 2. We already figured that out. That would be 5/4 into 2 squared is 4 minus 1. And that would be 15/4 feet pounds. And there it is. Really not that bad at all. Another example, A spring has a natural length of 6. A force of 2 pounds stretches the spring half a foot. So here K is 4. So my force for the spring is 4 times X. In part A, again the same deal. Find the work done in compressing the spring. Now the reason we're using the integral, you'll notice if you stretch it half a foot, if it takes 2 pounds for the first half a foot, that doesn't mean the next half a foot will take 2 pounds worth of force, because as you stretch the spring it becomes more resistant, or you compress it, same thing. So here we want to figure out compressing it from 5 to 3. Well, if its natural length is 6 and you want to compress it from 5 to 3, isn't that from really 1 and 6 to 3, from 1 to 3 of what? Well, we already figured out that the stiffness of this spring is 4. So this is B, 4x squared over 2 evaluated from 1 to 3. Work will be 2 times 9 minus 1. The work done would be 816 feet pounds. And if we go for B, how about if you want to stretch it from 8? Again, it's at 6. If you want to stretch it from 8 to 10. So if we go beyond its natural length, that's really stretching it from 2 to 4 with respect to 6. 6 is like the 0. So whether you compress or stretch, it's the same work. And again, once you get that part, it's pretty much set. The calculus is the same. That is really 2x squared evaluated from 2 to 4. Work would be 2 times 16 minus 4. That would be 2 times 12. That would be 24 feet pounds. Now what if you switch the order? That is, what if you look at this and says, if the work required to stretch a spring 1 foot beyond its natural length, work is the integral 1 foot 0 to 1 of f of x dx. Well, that is the integral from 0 to 1 of kx dx, because we know that the force is kx. And the work takes 12 feet pounds. Well, first I need to figure out k before I could go for the second part. This is k. K is a constant, x squared over 2 evaluated from 0 to 1. So that is k over 2 times 1 minus 0, and that is 12. So I have k over 2 equal 12. So k in this case is 24. So we know now that for this system, F equals 24x. Now if I go for the second part, it says, how much work is needed to stretch it 6 inches beyond its natural length? I missed an L in there. Well, 6 inches, since everything's in, if everything's in inches, you could give the answer in terms of feet pound. You could say inches pound if you want, or convert it. But since this is already in feet, 6 inches is really half a foot. So you're trying to figure out how much work is needed in stretching the spring from 0 to a half, and we know it's 24x dx. That would be 24x squared over 2. That would be 12 times 1/4 minus 0. That would be 3 feet pounds. And this is where we're going to stop.